please. We'll start again with the second talk. So we have Francisco, who's coming from Queen Mary again, who the title I've forgotten.
That's all right.
That's all right. So
I'll
we'll
remind
present
people.
the title right now. So please.
Let me just get some chalk. So, hello everyone. Is the mic working? Hello, hello, hello. Perfect. Great. So today I'll be talking about, is it okay if I write in yellow? Can everyone see? So about finite group. So finite group gauge theory on graphs. On, well, digraphs, directed graphs. Yeah, so this will be based on a paper that you can find on arXiv as of a couple of weeks ago. So this is 2503.17301. Okay, so what is the motivation for this project? So here what we wanted to do is to look at, so if we have classical field theory, right, and gauge theory on a classical spacetime, so gauge theory is well understood, and on the lattice as well, right? So if you have classical gauge theory, so here essentially everything that we have, I'll do a quick review in a bit. But here we can use principal bundles and connections on these principal bundles. So we have a principal bundle over M, so our manifold and principal bundle. Principal bundle just means that locally here this looks like a cross product of the manifold in some Lie group. And we have here, of course, a right action of the principal bundle. Then in order to construct gauge theory, what we want to look at is what's so-called, so if we have a local set, an open set in M, we want to consider a connection. So this will be just a Lie algebra valued one form that then has a curvature, which is then valued, which is then a two form. And what will be important for us today is also that, writing too big, is also that, so we have gauge transformations. These are just functions from this open set to the group itself that act on these two in some specific ways. And we also have what's called the holonomy. So this is usually defined as the path ordered exponential of the integral of the connection over a path. So what this means, this will be in the group. What this means essentially is that the connection will give you, so to speak, a parallel transport system, and the holonomy along this path just tells you how things, so for example, so elements of your associative bundle and so on get parallel transported along this. Is this familiar to everyone? Great. Yeah, so what we'll need more is, so we need a metric. So this is just G in omega 1 tensor omega 1, something M. And this metric induces a product on K forms. So we have omega K tensor omega K going to C infinity M, which is just a way of contracting the metric with K forms. I'll not reveal it. Review it. And then having all of this mathematical structure, we want to encode the physics, and the physics are usually encoded through the action functional, which for us is the Yang-Mills action, and this will look somehow something like this. So it's 1 over C. This is called the coupling, so how much particles interact with each other. Then we integrate over M, and we have some trace operation on the Lie algebra. And we will apply then this inner product to the curvature, so f star and f. So this will give us a function. So this will be valued in a Lie algebra tensor the functions, and then we take the trace to get some element, so function on M, and we just integrate it. Right. And then what we'll be looking at today as well is that quantum field theory, so what we want to do here is to define a partition function so formally speaking, we have, so the space, this I'll call the space of connections, and we quotient it by the space of gauge transformations. These are these elements here. Then we have some sort of, then we have some sort of integration measure over this space. These are just equivalent classes of alpha. And then we have, and then we multiply this with e to the power of I and then our action. So this is the thing that we want to define, and having this, then we can compute expectation values and so on. Classically, this sometimes gives problems because here we're working with infinite dimensional spaces and so on and so forth. So, but there's like techniques to handle this. And what I wanted to mention as well is that, so here we have the I. This is for like the Lorentzian signature. We also can instead write the exponential of minus s in Mills. This is when you're working, for example, in Euclidean space. So this is more or less everything that we need in order to make gauge theory kind of work in the continuum. Any questions so far? Feel free to just interrupt me. I mean here. Yeah, so sorry. So here I would have so here so this here it just looks like f star wedge Hodge star f, and then you just get the usual determinant of G. Yeah. Does that make sense? Right. So now if we go over to lattice gauge theory. So this is it's quite nice because so lattice is, you can just imagine that we have a square lattice. And this was kind of invented so that it would deal with a lot of problems that we have here. But in the lattice, if you're not using non-commutative geometry, you don't really have geometrical notions of all of these things. So what people decided to do on this side is to, instead of working with connections and its curvature, sorry, I'm moving around a lot. Instead of working connections and curvature, they decide to work directly with these holonomies. So what you do is you have a holonomy field, so to speak. This is a function that goes from a set of edges to the group. Here, this can be either a Lie or finite group. And then you have, again, the set of gauge transformations that goes from the set of vertices X to the group. And yeah, and I didn't write this here, but the way that this holonomy transforms, if we have here x0 and x1, then this transforms as just multiplying this holonomy with the value of the gauge transformation at the beginning, and you have the holonomy, and then you have the value inverted at the end. And here they do the same. So here we have, so for example, two vertices on a graph. We associate a holonomy here. And to each point, we then get some value in the group, right? And we have that this holonomy transforms exactly in the same way. So we have that u gamma x going to y is equal to gamma x, u x going to y, and then gamma y minus 1. And having this, you can then define an action. So this is what is called the Wilson action. which is then given by, so you sum over all representations of this group that you have, so irreducible representations. Then you have, again, the couplings. So the representations, as we're summing over them, they don't really interact with each other. So you could just choose one that you want to focus on. And then you have, so for example, if we look at the square lattice, we're summing over plaquettes. And then we have here the character in a specific representation of the holonomy around a plaquette plus it's going the other way. So we'd have something like this. And the motivation for this is that if you take, so if you take this spacing between the vertices to go to 0, then you can recover this in some sort of limit. Now, having this background, what we thought we would do, so then having this, you can then do QFT as it's here. Do you have a question? Yeah. No, go for it.
So E is the edge or that.
Yeah. Exactly, yeah.
Oh, okay, so U was holonomy?
Holonomy. Exactly. Sorry. Yeah, so if you take carefully the limit where the spacing between the vertices goes to 0, then you get back this action here. But there are several actions on this side that can give you this one, so you don't really have a canonical one. And what we thought we would do is to try to tackle this with a non-commutative geometry, because this gives you like geometry on graphs and on finite groups if you want. And so our idea was to try to kind of join the two approaches. So to try to use this machinery to just go to the lattice and see what comes out. Any more questions? Yeah.
In terms of the divergences that you have to work with these plaquettes here?
Yeah, so here, for example, if you have, I think you lose ultraviolet divergences, right? Because ultraviolet is when things are very close together, and here you wouldn't. But... Okay. So now let's review quickly how we do geometry on graphs. All right, so here we want to have, so again, we have set of vertices X and set of edges E for a specific graph. And then we take our base algebra. So this would be, so this graph would then be our kind of space-time manifold to be just the algebra of functions on the vertices. And this is then spanned by the delta functions on the vertices. Sorry. Right. And now if we want to construct a calculus here, so the calculi on this algebra are then in one-to-one correspondence with a set of edges. Sorry. So what we would get here is, so omega 1 is then a module by module over B. So this is just a span of E y for E y in E. And the differential going from B to omega 1. Here we would just write, so the f for f a function in B is just, we sum over all arrows. F then evaluated at epsilon, and then f evaluated at x. So here we're just looking at the difference between these 2 points. And then E of x going to y. And this calculus has a neat structure in the sense that it is inner. And what this means is that if you have a differential applied to f, you can compute this via theta via the commutator of theta with f, where theta here is just the sum over all the basis vectors on the calculus.
Here on finitely endless loops.
Yeah, so if you describe it like this, everything is finite. In order to do infinite graphs, you need to go to discrete groups, and there everything works. So if you have like the discrete line, that would, we'll look at it later. But yeah. Great, and now you can, let me delete this. So now we can extend this to a whole exterior algebra, and there are several ways of doing this. But we'll only look at one, right? So we talk about the minimal calculus. There's also maximal calculus and two other in between. But today let's focus on this one. This is essentially the tensor algebra over omega 1. Of omega 1 over this basis. This just means that we're taking the tensor product over this algebra, and then with some relations. And the relations here are just that if we look at two paths, so a path going from x to y to z, and here we fix x and y, x and z, and we sum over y. We want that this is equal then to 0 for all x and y. Sorry, for all x and z. If you look at other calculi, then you'd look at other sets of x and z where you'd put some restrictions where they might be connected to each other or not, etc. And something neat about this calculus is that it continues to be inner. So if we have any form in here, then we can still write the differential of this form as a commutator between theta and the form itself, where this thing, so this is now the anti-commutator. Commutator. Okay. Questions? Right. This is minimal because you have the maximal set of relations. So the others are. So for the maximal, you take all of this for all x not equal to z. I think.
Sorry, why is this minimal? Like, can't I take the zero prolongation, for example, of omega 1?
Sorry.
I think they just take the omega 1 and then omega 2 is 0, omega 3 is 0, and so on.
Yeah.
That's been okay.
Okay. Yeah.
I mean,
So
I know
this
it's
is-
trivial.
Sorry.
Never mind, never mind.
Yeah. No, you're right. That would be minimal as well, or even minimal, more minimal than this. I will pass the blame to Sean because he chose the nomination.
Good choice. Good choice.
Yeah. And the max is not inner. So there's other calculi that are smaller than this. Okay, now.
I can say this is like the analog of the Voronovich extension for a bicovariant calculus and a half fill.
Not necessarily, almost. Because I can never say the name, but that calculus is, you need to impose more relations on this thing. Yeah. So all that we're doing here, this works also for finite groups. I'll probably not get to them, but yeah. Okay, so having this, we can then construct a metric. So for a metric, we want, it turns out that we can just write this. So this will be just an element in omega-1 tensor omega-1, which we write like this, Cx. Right, so this is the metric. This is a metric tensor that we're looking at. Here we have x and x the same here, so technically could have a z. But with what I'll explain to you now, it will imply that this metric is central, meaning that multiplying a function from one side needs to be the same as multiplying from the other. And I forgot to tell you here the module structure of omega-1. But so here the module structure of omega-1 would just be f. When you multiply it from the left with the basis vector, you just get fx. So f evaluated at this first point, and when you multiply it from the right, you get just f evaluated at the end. So for a metric, as a tensor, we now want to build the inverse metric, and this would be a bimodule map. No, go for it. So this for now can be a complex number, yeah. But we want to put some conditions on the metric, and the first one is the reality condition, which is flip. So since we're working over C, we just have the complex conjugation. And if we imply flip G is equal to G, then this just means that these weights will be real numbers. And then if we imply if we want this to be non-degenerate, we also want these to be non-zero.
Whenever there's an edge, there's also the converse edge, right? Because otherwise, your E.
Yeah. So bidirected graphs. And here we're also not taking any edges between vertices and themselves. Right, thank you. So we have this metric, then we have the inverse metric, which would be a bimodule map, going from omega-1 tensor omega-1 C of x to C of x, which is inverse to G in the specific sense, namely that for any one form, we would have this identity. And this essentially means that if you write it down, it's the same thing as having classically that G mu nu G nu sigma is equal to delta mu sigma. So this, and then the other side. Right. So we're acting with this on the first element of G, and from the other side, we're acting on the second element. Good. And if we have this form, and using that this is a bimodule map, and so on, we get the form that this applied to two basis vectors is equal to, so some coefficient lambda going from x to y, and then delta x, x prime, delta y, y prime, and delta x. So this is a function, and these are just the canonical deltas. We get this form, and this is then related to the metric in the sense that this is equal to 1 over g y going to x. Okay, this is all known very well. Now, what we want to do is to, so before I was talking, so for the Young-Mills action, we want to have the analog of this, but now acting on two forms, correct? So the way we do this is very analog to this. So we just construct what's called a two metric or a two inverse metric. Let me. Yeah, so the two inverse metric would just then be a bimodular map, omega 2 tensor C of x, omega 2 going to C of x. And the general form that this has, so what we want for this is then reality condition, right? So here we'd have the reality condition that if we apply the complex conjugation outside is the same as flipping and then applying the complex conjugation, where here, of course, omega and eta are two forms. And then a proposition is that for something of this form, it will act on the basis vectors as, so here we just have a path going from x to z, two path. Here the same thing the other way around. This will then be equal to some weights, x going to y, going to z, going to y prime. And then delta x, x prime, and delta z, z prime, delta x. So we have these coefficients with the properties that first, if we're summing over four paths, so x going to y, going to z, going to y prime, going to x, of these things, this needs to be equal to 0 for all x and z. And this essentially comes due to the, where are they? Due to the relations here. So we just recover this condition on the weights. And then the reality condition just tells us that x, y to z to y prime is equal to the complex conjugate of switching y and y prime. Okay, and what we're looking at here is that I've only written this 1 to 3 step path, but here at the end we really have a for loop, so 4-step loop. So what this sort of map is doing on a graph is associating this weight, this lambda, to the loop x going to y, going to z, going to y prime, and going back to x, which makes sense. So if when we're talking about, this is because for here we have that x is the same as x prime, and z is the same as z prime, and then we have this path just going all the way. Right. So as we had before that the inverse metric on one form was related to edges, we see now that the extension of this to graphs is related rather to surfaces or to the, yeah. And we don't have a general solution for this kind of coefficients, right? You can just construct as you want. We could not find a way to relate them to the metric, but another proposition is that a viable solution for this is lambda x going to y, going to z, going to y prime is equal to a x z lambda x y, then lambda x y prime minus, write the minus here, minus delta y y prime, and then the sum of w x going to w x to so lambda x to w. So that everyone can see. So this solution, what we're doing here is that these are some weights that we can choose, whatever they are. Then here what we have is that if y and y prime are not the same, we just have really the quadratic form of the metric going in this way and in this way. So what you'd expect for the square. And then this part at the end, we need, in order so that this equation is compatible with this thing here. Okay. Any questions so far?
Yeah, I have a quick question.
Yeah, tell me.
So in this last proposition, under what conditions is this metric on two forms induced by the combination of the metric on one forms and some sort of embedding of complemented embedding of two forms as some sort of two tensors?
What do you mean? Sorry. So you're asking how this thing is related to the inverse metric.
So to be more precise, you have this metric, this inverse metric on one forms.
Yeah.
You plug in the star in the right place, you get a positive definite module inner product on one forms. So the inverse metric, when you plug in the star, the left argument, you get a positive definite algebra valued inner product on your right module of one forms, right?
Yeah. So
So then that induces by this so now that induces a canonical algebra valued inner product on two tensors. And so I think this is stuff that, for instance, I think there's examples of this in Edwin and Sean's book. If you now have an embedding, a complemented embedding of your two forms as two tensors,
yeah,
then you get an induced metric, nice induced metric on your two forms.
I don't know about this. Possibly.
I mean, if you can embed your mod, if you have an embedding of your module of two forms as a submodule bimodule of your two tensors,
yeah,
then a nice inner product on your two tensors restricts to a yeah. So if you have such an embedding, which you know, there's examples of this in the book, this sort of thing in the book, then if you have an inner product, an algebra valued inner product on the two tensors, that restricts to an algebra valued inner product on the two forms.
Yeah.
And then there's various conditions that you can require on how nice this embedding has to be. For instance, you could require that it be an orthogonal projection with respect to the induced metric.
Yeah, exactly. But I think that this embedding is not always clear what is happening.
So it's not definitely not in canonical. Definitely not canonical.
Exactly. Yeah.
So what I'm wondering is, are there any sufficient conditions that, or do you have an understanding for when the kind of metrics on two forms that you consider in this last proposition come from this kind of embedding?
No.
Okay.
Sorry.
Okay. No, sorry about the long-winded question. Thank you.
No, it's all right. Don't worry. Thanks for the question. Any more questions? How much time do I have?
20 minutes.
Okay. Generous 20 minutes. Sorry?
Not too generous.
Not too generous. All right. I'll try to keep it to 20 minutes. We're on page 3. Right. So, given 20 minutes, let's pass to gauge theory on lie graphs. So here we really want to just copy what I had in the middle board at the beginning to see what comes out. And I'll not go into too much detail about this, but for those of you who are familiar with the formalism of quantum principal bundles, so what we're doing here now is to take the principal bundle to be just the base So functions, so the base is just functions on X, and then we tensor this with functions on a group, where here G is a finite group. So this would be an example of a trivial quantum principal bundle, where the right action here is just given by the coproduct on the Hopf algebra on functions on this finite group. So now, given this formalism, we can define forms, so and-gauge transformations. This here will just, the way we would get this is just to look at, well, in Shan's and Edwin's book, to the formalism on quantum trivial quantum principal bundles. It's a mouthful. And you get this out, which is, so here we have that connections are just valued in CG plus tensor omega 1, because here we're taking the universal calculus on G. Right, and we are imposing a reality condition, which in our case will be that this is anti-Hermitian. And now for the gauge transformations, what we have is, so gauge transformations will be, you can think of them as functions on X with values in CG. So this is just Lie algebra valued one forms, and in the case of the universal calculus, you get that the Lie algebra of a finite group would be this. And here we have some conditions, which is that if we apply the co-unit to this element, we would get 1. Here the co-unit is just co-unit of G is equal to 1 for an element G of the group. And then we want this to be unitary, so we impose that its inverse is just the complex conjugate. Having this, we can define the curvature of this form and its holonomy. So the curvature here would just be a 2 form that is defined like this. So identity tensor D, this is a differential on the base, so on this omega 1. Alpha plus just the wedge product of alpha with itself. And here what we're doing is just taking the wedge product on omega 1, and then just the usual product in here. And this would be then a CG plus valued 2 form. Right. And what we have now is that we can define, very analogous to the classical case, just so the gauge transform connection is just gamma alpha gamma star plus gamma d gamma star. What this turns out to be is then if you write alpha is equal, so if you write it in the basis, so alpha x going to y tensor e x y, where this here is in CG plus, then the gauge transform connection x to y will look like this. So you get just the first term, which will just look like this, and the second term, if you write down the differential and so on, do the calculations, you just get the product of so gamma at the beginning and at the end of the arrow minus the identity. Right, and if we have this, then the curvature transforms exactly as you'd expect. Right. In this case, we can also define the holonomies. So for the holonomy, if you remember, the holonomy was just the integral of some exponential. And the idea here on graphs is to just take this up to first order. So the holonomies here would just be, we define this as U being equal to E tensor theta plus alpha. So if you have an exponential, this is just really the two first terms of the exponential, which means that ux going to y will just be equal to 1 plus alpha x going to y. And it also transforms as you'd expect. So as I showed you before. Very well. And now we actually, like from now on, since this transformation is much nicer than this transformation, this here, we'll actually work with this from now on. So here we define our space of holonomies as just U in CG tensor omega 1. Here we have our reality condition again. And this condition, so co-unit times identity U is equal to theta. This is just because if we apply this co-unit here, here we'll just get 0. So we just get, and here we'll just get 1. And this turns out to be isomorphic to 1. I mean, just a shift. And in this case, the curvature gets a quite nice form, which is that f is simply u wedge u. So it's very simple. If you take the other calculi that I mentioned before, then it will get a bit messier. But we can compute this. But in this case, just f, it's just u wedge u. And then we can just construct the Yang-Mills action given everything that we already have. And so this we would define as the action being integral over x. I'll explain what this integral is in a bit. Sum over non-trivial representations, 1 over c rho, and then again, this is again the character, and we have then this inner product that I introduced before, applied on f star and then f. This integral here is just, if you integrate the function on the graph, we just get the sum over all the values everywhere. And we exclude here the trivial representation because for trivial representation is essentially applying the co-unit, and applying the co-unit we know we have said everywhere. So here applying the co-unit just gives 1 or theta. Yeah, so everywhere we've specified what the co-unit is. Yeah. Sorry. Okay, and now if you have this form, if we introduce what's called the Wilson loop, so Wilson loop would be, so omega in a specific representation of a path, so of a loop, so x going to x2, x3, etc. until it goes back. This will just be the, sorry. Yeah, so this is just the character of the holonomy that you get going around this loop. So u x1 going to x2, etc. until u xn going to x1. If we define this as such, then the form that we get for the action, functional, is the following. Is essentially what we get from the Wilson action. So the theorem is then that S for the minimal calculus is then equal to minus rho not equal to 1, and then we sum over 4-step loops. And then we have our couplings. And then our weights, and then the Wilson loop along this path. So you get this action. What this means is that we have a lot of loops appearing in this action. And examples of these are just X and Y. So we could have loops that just go back and forth. This is fine. We can have loops that just look like this. So this would be the case of like trivial loops. But then you also have non-trivial loops where it just every vertex is different, where you just have these squares. And this is exactly what we saw before in the Wilson action. So if we take everything from non-commutative geometry, we get back exactly what, well, people use in lattice gauge theory. One thing that I wanted to note here is that here we're working with a group algebra, right? So we have u x to y is in the group algebra. And the reality condition tells us that u x to y is just equal to u star of y to x. So going the other way around is just the same as taking the complex conjugation. And then if we restrict this to the group inside the group algebra, we would get back lattice gauge theory. So this would be G-valued lattice gauge theory. And in this case, so for u x to y in G, we get that this is exactly the inverse. If this is the inverse, sorry, y to x. If this is the inverse, then this will just be the identity. So this just kind of vanishes. This vanishes as well. So the only things that matter are these ones, because these will not count for the dynamics of the theory, so to speak. So in the case that we restrict our theory to lattice gauge theory, we get exactly the Wilson action. How much time do I have? Generous 5. Okay. Well, this takes me too long to introduce all of this. Okay. Then I want to give you 2 quick results. So first is that we can compute moduli spaces, namely, so if we start with a G abelian, so an abelian finite group, then we have that the moduli space, this is just a detail, is equal to R bigger than 0, E0 cross U1 L, G minus 1. So this means where L here is really equal to E0 minus X plus 1. So here E0 is a set of undirected edges. This is a set of undirected edges, meaning that we're not overcounting these two. This just counts now as one edge. So what's happening here is that essentially for every undirected edge, we get a positive valued field, so to speak. And then this bit comes from if we take any graph, and if we take a maximally spanning tree, right? This will be exactly the amount of edges that are not in this maximally spanning tree. Meaning that, for example, this is for a planar graph. So here, for example, we get 3 positive valued fields, so to speak, or positive valued omega. Sorry, positive valued numbers here, and then we'd get a phase going around for this placket. So this is the meaning of this. And we also have something analogous for non-abelian groups, which is a bit more complicated. What is happening here essentially is just a polar decomposition of things. Well, since I have 5 minutes. Sorry for that.
This technical term is for G abelian.
For G abelian, yeah. Yes. Okay, now, just to give you one last result, if we look at the square, so if we look at the base being Z2 cross Z2, and then G being just Z2. Okay. So what will happen here is that, so we have this square, meaning that this is just 4 real modes and one going around. And what we have here is that we have our non-commutative theory, right? So we have C, so Z2, let's say non-commutative gauge theory. And inside this, we can find U1 lattice gauge theory, and we can find Z2 lattice gauge theory. Okay. Now we can look at, we can do quantum field theory on this. So observables in KFT. If we look at the observable of this phase, if we take the Euclidean theory, this means that everywhere we just take the metric to be 1, right? And we look at the expectation value of these 3 theories, which we can. We'll get that the expectation value of Z2 of the lattice gauge theory start here and kind of then go to 0. This is with respect to the coupling. So this would be the weak limit, weak theory limit, and this is like the strong theory limit. So here I'm showing this. This would be for Z2, lattice gauge theory. And then for the U1, it would go a bit slower, but still the same shape. And then for the non-commutative geometry, what happens, so this is U1 lattice gauge theory, is that somehow these new modes that we have, so these new positive modes, suppress the expectation values a lot. So we see that when we go to the strong theory, this just kind of gets really suppressed. So for the Euclidean, everything works well. If we then look at the Lorentzian case, which should be here having so a positive metric for the time-like, positive metric for the time-like edges and a negative metric for the space-like edges. In our case, we still get something for the expectation value of the phase. Like this would look something like this. So the absolute value of the expectation value of the phase for the non-commutative theory. But if we try to do this for the lattice gauge theory, we would get in both cases just something that is full of divergences all over the place. And so what we think is happening here is that the presence of this new field, of this new positive field, is kind of regulating the whole thing. So if you do, the takeaway message is if you do lattice gauge theory on a Lorentzian square, then what you get is a bunch of divergences that don't really make, well, at least I cannot make sense out of these. But if you do this with our formalism, then you actually get properly valued expectation values. So thank you very much.
We have questions, comments.
So do the non-plaquette loops basically serve to regularize?
Yeah. So it's not only the non-plaquette loops, but it's essentially both the non-plaquette loops and this one.
Okay.
Right. So because going from here to the U1, you can see that it's just setting these values to 1, right? Because then you get the U1s here. Yeah. So these sort of, I don't know if it's exactly regularizing the usual sense of renormalization, but yeah, it kind of regularizes the expectation values in this way. So it gets rid of these divergences.
Okay.
Yeah.
Thank you.
No worries.
Yeah. So this theorem kind of answers the question I was going to ask to some degree, but I was wondering to what extent properties of the graph might be reflected in the structures that you build, like
Yeah.
connectedness. I don't know.
So connectedness of the base graph. Then you just have two of these theories for. So you just have two copies of everything, right? Because the disconnected components would not talk to each other. If you take the other calculi, so I'm just going to write the names. So these other calculi then have where you had this condition on the tensor algebra, and if you take these other ones, these in the curvature will only look at squares, but for these other three, you also include triangles and other things, and you also see this in the action. So if you compute the action in these other variants, so to speak, then you also get triangles in the action and other terms. Yeah. So those things would be reflected, but it's mostly like squares and triangles. And I think the one that's called Met Prime was used by another one of Shan's students to relate this. So this was related to the fundamental group of graphs, but there I don't know how this works.
Cool, thanks.
Yeah, no worries.
Maybe I can ask a question.
Yeah.
So maybe first question. So you have trivial quantum principal bundles. So I guess this also says that your group is not acting on X, right? So this is really just this algebra, the total space algebra is just a tensor product multiplication. There's no action and something. So do you see your theory to extend to something more complicated, like smash product algebras or cross product algebras, where you have now also actions of your group on X? More complicated.
You probably could do that, but then it would not be necessarily gauge theory anymore, because you'd be acting on, like, you'd also include some sort of space-time symmetries, right? Or
I'm not sure what.
I mean, this works
mathematically.
Yeah, I think this would work as long as you have some sort of trivialization map for the principal bundle, which I don't know if you have in those cases.
Yeah, so for smash or cross products, still your total space algebra like splits into the
two
top algebra and the base algebra. Huh?
Yeah, that would be interesting to see, but I don't know.
And maybe a follow-up question. So there is this other notion of gauge transformations that are basically convolution invertible unital maps from the Hopf algebra into the total space algebra.
Yeah.
And you're saying this is the same.
This is the same.
Okay.
This is the same because so if you take gauge transformations like this, then convolution the convolution product just becomes the product in there. So it's the same. So everything here is derived from that formalism. Yeah.
And like also there, I think you asked that these maps are collinear or something, right? They are, but this you say
it's
automatic.
Yeah. So we use the definitions in that formalism, which is that this is unital. So you want
no, I'm not saying unital. I'm saying collinear.
What is collinear?
So there are coactions on those spaces. But I see you don't have.
But we don't have a coaction here. Yeah.
Okay, because usually, if there's a coaction here, then you would also ask that. Okay, fine. Then this is simply not.
What you can also ask of these is that they are differentiable, and then it complicates things.
I see.
Yeah. So it restricts a lot what kind of maps you can have here. Essentially, so if you ask them to be differentiable, then you know that, so instead of gamma being valued in CG tensor CX, you just have G here. So you didn't have the group algebra, just have the group itself. Yeah.
Okay. Thank you.
So if I understood the definition of, to go back where you start, the definition of the calculus you've got for every 2 points, you've got an arrow going in this direction and the other direction.
For every 2 points?
Yeah.
Yeah.
So what you can do then, paper I was reading recently, is because the star map is the one that's just going to change the
Yeah.
direction of the
Yeah.
graph. Yeah. So
Yeah.
if you number, okay, assume it's to find a graph and you number them in some, you put a total order in
Hmm.
1, 2, 3, 6, then you can get a first order complex structure under one forms where, you know, so what is a first order complex structure? It means that you decompose your one forms into these holomorphic and anti-holomorphic.
Mm-hmm.
But it's just a decomposition, a directional decomposition, such that the stars, which is this guy, this guy. What are they? It's going to be the ones that are pointing up, give you the holomorphic, and the ones that are pointing down, the anti-holomorphic, or vice versa. And then from this, that should extend to an almost complex structure on the whole thing, in the sense of Edwin, who introduced it many years ago.
Mm-hmm.
And then you can start to look for Kähler structures, which would give you metrics automatically.
Oh, on
the whole thing.
On the whole thing. Yeah.
Yeah. And sort of like giving a different point of view on the question that you were asking about degree 2 metrics.
Yeah. Okay. Okay.
So
I didn't know that.
More a comment than a question.
Cheers.
So said for a question before Mauro gets to it, like, what about jets? As you spoke about the last time you were here, I mean, you can look at jets for these things.
We could. We haven't. No. So now what we're doing is we're looking at the variation of Y complex, if that tells you anything. Great. So you could look at the, if you have a manifold, or if you have a vector bundle now, you can extend this to the jet bundle, or to the infinite jet bundle. And then if you build the RAM complex in here, it splits into 2. And this is kind of where we got stuck last time. And this splitting into 2 into kind of vertical and horizontal bit is what then gives you, in physics, the Euler-Lagrange equations, and so on and so forth. We are now trying to apply this to the very simple case of just, so the base being Z and then cross Z. So yeah, this is the simplest place to start, and then we try to, this essentially gives it, so the space of sections are just functions on Z, and then maybe you can extend so that this space of sections is just these forms, so these connection forms. But I'm not sure now exactly how that would start. Yeah, thank you.
Any more questions? Anybody online? That appears to, actually, there was one question. I had a last one. What about connections for these things and bimodule connections?
Yeah, so this thing induces bimodule connections on the associated bundle.
So you have a principal connection that induces yeah, okay.
Yeah.
Okay.
What else do you want?
What if these are bimodule connections?
I have checked it for if you take an action on like functions, then yes, I think so, if I remember correctly.
But if your principal, so if you think about it in terms of the capital pi, Shan would write it, that projects from your vertical to, from your total to vertical, and then if that's a right A module map over your algebra, then the associated connections will be bimodule connections.
Yeah. So this comes from that pi in some way.
And it's in some way, but is this pi a right module map over the algebra of the base?
Here.
Yeah.
It should. I haven't checked.
Okay, well, in that case, you should get bimodule connections on the associated vector bundle.
Yeah, but I'm not sure there. Yeah.
Okay.
But I know we get bimodule connections on the associated vector bundle, so.
You do get bimodule connections on these things. Okay, okay. And in particular, bimodule connection on the calculus.
Of the base.
Yeah.
Yeah.
Yeah. Okay.
Yeah.
Very nice. Because then if
no, sorry. Yeah, I mean, if you take probably
Probably. Okay.
I checked for a general associated bundle, so I guess on the base as well.
And is the calculus, it should be an associated bundle? No?
Yeah, should be.
Yeah,
Should be.
And then if that calculus is torsion free, you get a description of the maximal prolongation in terms of the bimodule map.
I will agree with you there. Yeah.
So,
yeah.
okay. So if we have no more comments, I think that's a place to
Thank
stop.
you.
We thank Francisco again. Now, next week, do we have the slides, Karen? We have our very own Arnab Bhattacharjee, who will make the journey from Caerleon, like every Tuesday, to speak about Custance differentials and quantum Grassmannians. So that's an approximation of the title. What is the actual title? Q deformation of the Custance differential for the A-series irreducible quantum Planck manifolds. So hopefully we'll see you there.